Okay. Alright. Everybody has submitted the assignments? Alright.
1 minute delay.
Fine, there's still time, I guess. I kept the deadline a little, maybe 26th or something. It's cut off date, which is cut off. No, you can still submit. I kept it because I uploaded it little late. Okay. How did you find the assignment? The problems.
How did we solve it or find?
How did you find it? How was it? I kept some problems in the last question.
It was a little bit long, but it
Very simple.
Like forced us to understand what was about.
Yeah, this is how I
like it.
Okay, very good. Alright.
The last question was a bit how to find 5 examples. All the good examples we already talked about in class.
Oh no, they are. You can find 100 examples.
Yeah.
This is why I gave 5. Initially I wrote 10.
Yeah.
10 or 10 will be too much. I was kept it 5.
Can I say something?
Yes.
The part about the exercise that you said we have to submit it in handwriting. That
Yes.
was honestly really, that added a lot to the time it took, because I understand the concern about ChatGPT, but
That's the only concern. See, it's not your problem. I also have a problem in checking it. I don't understand everybody's.
yeah, that's it. It makes your life harder, and if you really wanted to use ChatGPT, we just copy it to the paper, so it doesn't really do anything
The
anyway.
logic is, even if you copy with ChatGPT, which I do not recommend.
Yeah, no, absolutely. I'm talking about the hypotheticals too.
Okay, ChatGPT is not bad. Okay, it helps you in learning. We
Yeah.
should use artificial intelligence in creative manner,
Yeah.
which is fine. But if you see something and then write it, you will still learn it. So that's the logic.
Yeah, sure.
I think it's okay. It's not a problem. It's fine. You will get used to it. Okay.
Sure.
This is number 1. So we'll quickly review what we learned in last lecture. You are new? You were not here last time?
No, I watched the YouTube.
Okay, so we will review it anyway. Because the first and second lectures of hydrodynamics are going to be the most important ones. Because it is the very basics. After 20-30 years, if some student comes to you and asks you any question about hydrodynamics, it will be all about first and second lecture.
Yeah.
Later on, whatever we learn, that will add to the expertise of the subject. I don't know, how do you write the equations on the laptops?
What?
When I write the equations, how do you write on the laptops?
I work with Chat. I tell him what the equation is. He works in laptop.
So you write in that. When I write it, you will write it.
Last time it was very
Yeah.
I think pen and paper is much. You making your life harder as well.
I don't think why. I got used to typing it. So.
All right, great.
Why not?
What's the issue?
Just a good there. What do you need?
Okay.
It's okay, fine.
What's the issue?
Okay. Thanks.
Okay. So we quickly review whatever we learned in 20-30 minutes. Then we go on to today's lecture. Okay? Because if you miss the basic concepts of first lecture, if anything is missing, then you don't understand anything later on. Okay. So we studied what is a fluid. Fluid is a physical entity where many particles or bodies are interacting together. And the mean free path of interaction is much smaller than the scale of the system. Like if you throw many balls together, they are not a fluid. But if you throw balls together with 1 kilometer large, let's say cannon, it will behave like a fluid. Because then the mean free path is much shorter than 1 kilometer. Okay. So we learned a couple of concepts like continuity equation, where mass of the fluid happens to be conserved alongside a closed surface. This is a very standard figure that you will always keep in mind. A fluid is moving, and we imagined a 3-dimensional volume element in which the particles are entering and going out. We try to see how the continuity works here. Mass conservation principle. we find out that the rate of change of mass which goes out of the volume element is given by the rate of change of the volume integral of the density. This is equal to negative of, now this is volume integral, integrating over whole volume of this body, and this body has three-dimensional surface area. So the flux that goes out of the surface area, it was minus of when F is the surface area of the body. Body not necessarily has to be spherical. It can be any arbitrary body. You converted this integral into volume integral. Let's call this volume as V0 because small v is for velocity. And then we concluded from here that taking ddt inside, it gives us the continuity principle that I will write here. Okay. This was the equation of continuity. Okay. What this means? What is the physical meaning of the equation? It means mass cannot be created. Very simple, very basic. Or, in other words, no mass has been added from outside of the system. Number of particles or the mass which is contained inside the body, whatever mass enters inside, it has to be equal to the mass, whatever mass goes outside of the volume has to be equal to the mass which is flowing out. This we have written in terms of the language of mathematics here. Alright. After this, we derived Euler's equation. One more thing here. This quantity rho v, this is called mass flux. Why it's called mass flux? The flux of the mass which is going out to the body. Alright. Euler's equation. Euler's equation deals, it's an equivalent equation of Newton's law in classical dynamics. When a body moves, F equals ma. You are familiar with that. Force equals mass into acceleration. But a fluid is a complex entity. Many particles are injected together. So we found out that it's not as simple as F equals ma. It has to be written in different form. And we came up with the understanding of pressure. What is pressure? Force per unit area. If any fluid is flowing, you have a surface area. Like here, the molecules are colliding with my hand. This is area. Every molecule of the gas, air, is putting force on that. Okay. The per unit area, how much force is being put up, is called pressure. Okay. So force is basically on a certain area, what will be the force? Let's call this F because we keep the partition cell. If there is a closed surface, the same sphere, we write the force in this form. What is the mistake in this expression?
I'm sure it's not a vector.
What? Pressure is a tensor though. Fine. We will see today in the mass, the momentum flux, pressure is actually a tensor. Second tensor. Anyway, here we will treat it as a scalar. So, what is the mistake in this expression? Minus. Minus.
Yeah.
Why there is a minus sign?
It's
Why the force is negative?
the force exerted by the system outside, not the force exerted on the system.
What is the system?
Thinking.
Open surface, right?
This is my hand. Huh?
It's an open surface. It's not like a.
This is my surface. Okay.
Yeah.
Why the force acting on this surface is negative? Fluid dynamics is all about having a good picture of the system.
This is the integral that measures P, the pressure.
Forget about integrals.
No, I'm trying to
Let's say-
understand. I'm trying to understand just the picture.
Now it's differential.
Okay.
Small area element, dF, force is pressure into area element. Why it is negative?
Oh, because the area vector is coming
Area vector is
outside,
outside. This is area vector.
and you want to push it inside.
And the force is putting it inside. Okay? Alright. And what force is? Mass into acceleration. The basic principle is the same. The representation is different in fluids. So this is, I converted this into volume integral. Grad PdV, the pressure gradient, using the divergence theorem. Now, the problem here is that mass is not exactly well defined in fluids. If an object is moving, we know its mass, let's say 15 grams. But how about the mass of the fluid? Fluid. This is why we deal in terms of density, mass density. So we find F0, which is force over volume. Okay?
Why it just not defined by the sum of the small masses of the entire molecules? I mean, why it's not well defined?
Mass is defined. Suppose the river is flowing. Okay? Now rivers, different parts are not connected together. You want to find out what is the force on the river at a certain point. We took the example of a balloon. You plug the balloon, it's going out, whole balloon is expanding. Take the example of blast explosion, it's expanding. At a particular point, how will you find out what mass it has? Because the force is on a point. If I apply force on this object, where is the force acting? Force is acting everywhere, right? But there is a center of mass. We treat it like the whole force is on the center of mass. Is there a concept of center of mass in fluid? No. That's the problem. Okay? But still the equation remains to be the same. This is why it's kind of force density. Okay? Per unit volume. It's customary. So force per unit volume is simply minus gradient of P, because volume integral comes out. And this is mass into acceleration. Acceleration is acceleration. Mass per unit volume is density. Rho I, which is rho dV dt. Okay? And I showed in last lecture that dV dt also has very intuitive physical meaning in hydrodynamics. It's not like just rate of change of velocity with time. Okay? It's because the fluid has two properties. All elements are different, all the points are different. So velocity depends on space and time both. So I showed in last lecture that dV dt is represented as partial velocity with time V dot gravity. Remember this? This is how acceleration is represented in fluids. So we use this here, and the equation turns out to be this is Euler's equation in absence of any external force. What if there is an external force?
Then you add it on the side forces.
If there is any external force which is creating any external acceleration, like gravity,
You add the
if the smoke is going out of the incense stick, you burn the incense, you know incense stick, the smoke goes out. When you burn it, anything, if you burn anything, it will produce smoke. Smoke will go out. But that smoke, the force on that smoke will be governed by the pressure gradient. But it is in gravity as well. So you just add any external acceleration that it has. A is acceleration. If it's gravity, it is G. Okay?
Don't we need to multiply it by the density, or
Hmm?
don't we need to multiply it by the density?
We divided the density here.
Oh.
Come on. You need to. If you put the density here, then it will be density. We just divided. Alright, so this was Euler's equation. Lastly, what we had? Bernoulli's theorem. Bernoulli's theorem or Bernoulli's principle. What is Bernoulli's principle?
energy locally is conserved because
If there is no external addition of energy in the system, for an isentropic system. We also wrote this form of equation for isentropic systems. What are isentropic systems?
systems that don't exchange heat and conserve
Entropy
Simple
constant.
and adiabatic.
Adiabatic. The system is isolated. It does not exchange any kind of any energy with the surroundings. For them, we wrote rho dV dt, no, only dV dt equals minus grade U. W. What is W? It's enthalpy. Okay? Do you understand what actual meaning of enthalpy?
I just wanted to ask for that clarification.
Yes.
Enthalpy includes the energy, like internal energy of kinetic energy, potential energy, all of that,
Yes.
and it also includes the like energy that took to do work against the ambient pressure to, like depending on the volume of the system.
Yes, it does.
So it's like a potential. It's like I have potential energy, and the fact that I occupy this volume, I can use it, and then so it's okay. It's a measure that's useful for systems that change volume.
It's total energy. Imagine a river is coming from the top of the mountain. It's always good to deal with in terms of examples. When the river is coming, the water in the river have two types of energy. What energy is water in the river have? Gravitational, okay, gravitational energy of course. But let's forget about the gravitational energy. Other than that, what are the two types of energies the water has?
Internal and
Other than
Heat.
are we talking about internal and the volume
internal.
thing?
Yeah.
Molecules inside are interacting with each other, so all the molecules have energy. Once you add all of them, that's the internal energy of the system.
Okay.
And
It has the
it's
energy.
falling down, it's kinetic energy, it's doing work. Okay? We'll look into it, okay? Today's lecture we will start with the physical meaning of W. We'll have a good intuitive understanding of that. Bernoulli's theorem, we found out that this is constant, half V square plus W. Half V square is kinetic energy per unit mass, and this is heat function per unit mass, which is enthalpy. It remains constant along the streamline of a fluid. Suppose this is the streamline. Okay? It's not along the coordinates. The streamline of the fluid, like a river is going in a certain path. You take the streamline coordinates, and this remains constant. There was an error in the lecture notes where I forgot to remove the gradient from here, so I just corrected that. I'll upload that.
Oh, you re-uploaded?
I haven't uploaded yet. Either I will replace the first lecture or I will upload first and second in the second lecture. Okay. Let us start. Alright. So now we understand this Bernoulli's theorem. So this was, in summary, our first lecture. Okay. Now let's start with the physical meaning of this W, enthalpy, so that you will have a good picture of what it is. Basically, it is energy. Energy is constant. Okay. Now we are in a little bit of thermodynamics. So we will go all together because thermodynamics is very important. By definition, enthalpy or heat function per unit mass is this. This is how we defined in the last lecture. It's the internal energy per unit mass plus P by rho. Now, as I talked about it right now, that it is basically the internal energy, which is the energy of the molecules interacting with each other. They have huge energy when you collect them together, plus the work done on the system. Yes.
This is energy, enthalpy, all of this is per unit mass.
Per unit mass, yes.
Because the rho you said is inverse volume, so it's what? It's not kilograms over meters cubed, it's 1 over meters cubed? Or
that was specific volume, 1 by rho.
okay.
Its inverse of volume is a specific volume.
Okay.
So this is why it is called heat function per unit mass.
Okay.
Okay. So how does it show that this is internal energy and this is work done? This also looks like internal, right? Pressure is internal, density is internal, internal properties of the system. How does it show the work done? Suppose there is a piston, a frictionless surface, and there is gas inside it. Okay? You push the piston from side, and it comes here. Okay? dx, distance. What are we doing? We are doing work on the system. Pushing it, pressing it, compressing it, we are doing work against the system. The pressure by definition is force per unit area. Force is pressure into area. Now, by classical mechanics, the work done is in this process F dot dx. You are aware of this? F dot dx. But F is pressure into area. Okay. What is F dx? F is the cross section of this. Cross section area, yes.
Can you just make your P and O a little bit different? I find it hard to distinguish between.
Okay, I will try to keep it all like that. Okay.
Yeah, thank you.
It's important because If it mixes up, everything will be messed up.
Yeah.
Okay. So what is F dot dx? F is surface area of the piston. Dx is the length scale of the piston. F dot dx is the volume up to which you have compressed. Area, this is volume. Or rather dV, the delta of volume which you have compressed the system, right? It's 3 dimensional. So basically this is E dot dV. So work done is pressure multiplied by the amount of volume you have compressed the system. And work done per unit mass, it will be over rho dV. We are aware this dm is rho dV. So basically dV gets cancelled, P over rho. So now we know that the work done per unit mass is basically P by rho. So the second term in the enthalpy is, it represents work done. Okay, even if it is shown in terms of the parameters of the system itself. So what it signifies is how much work per unit mass is required, and that defines what is the total enthalpy per unit mass of the system. Okay, this is very important to have a clear picture of what enthalpy is. It will come over and over again.
Can you repeat that?
Hmm?
Can you repeat that?
Okay, enthalpy is the total energy of the system. We represented it here in terms of per unit mass. This is internal energy of the system, which is basically meaning by the overall energy of the molecules divided by the mass of the system. And we showed here that this P by rho, despite being the internal property of the system, internal parameters P and rho both, what it shows is the amount of work you need to do on the system. So this also represents in a form of W. Now P by rho is basically kind of temperature. So this is ideal gas law. Have you read it somewhere? In the schools, P equals NKT. And N can be written as rho by M. If it's monoatomic gas, the mass of the gas particle is M0. So P by rho is basically this P by rho represents the temperature, which means hotter the system is, more pressure you have to put to do work on the system. Okay? Any questions on that? Yeah. Euler's equation was, now let's move on to hydrostatics. What is hydrostatics?
Starting system to become
Steady state. No. It's more than steady state. Steady state means del T is 0. There is no time dependence. Suppose you fill the water inside bucket, leave the bucket here. The water inside the bucket is still liquid, it's fluid. And because intrinsically the system has fluid properties, Euler equation is applied on that. So how the Euler equation will work? You know the Euler equation? Hmm? This we know, Newton's law. This is already equation. Rho dv dt equals minus rate of p. If the system is not moving anywhere, total velocity is 0. Okay. In that case, in gravity, it becomes g. Basically, a is equal to minus g in gravity. Okay. Gravity always works outside the Earth's surface. It's z axis. So this grad p is simply okay. In static case, the pressure gradient goes like that. If you solve this, we need to put negative sign here because g is negative where?
Wait. Yeah, there's supposed to be an
Yeah, negative because the pressure will always decrease with height. Alright. So you solve this assuming that g remains constant with height. In short distances you can assume it to be constant. But in long distances it is not
Yeah,
constant.
no, for our purposes.
C0 is constant of integration. Assume at the surface of the earth at z equals 0, assume p equals P0. There's a constant pressure on the surface of the earth. So we put it here, z equals 0. You find the constant of integration. C0 equals P0. Put it here. P equals minus okay. So P is actually P0 minus rho z. If the liquid is water or the fluid is water, let's say, the rho is constant, the density is constant. In that case, what you see is pressure decreases as you go up in the water. So if you take a bucket and fill it with water, what this equation means is the water is in hydrostatic equilibrium. It's not moving. So its pressure will decrease or increase with height. Z is height. Minus. Look at the equation. It will decrease. The pressure goes down. What it means? Now we did mathematics. What it means for the water?
It just means there's more water above it, so it will be under more pressure. You can imagine like a column of water above pushing down you.
Say it again.
When you are low down in the bucket, you have more water above you pushing.
Do you know swimming? Who swims? Do you know swimming?
Yeah.
When you go inside the water, what do you feel? Feel high pressure. Yeah? There's a certain height you can go down below. A certain height you cannot even tolerate that. This is what it means. You go down, pressure keeps on increasing. As you go up, pressure keeps on decreasing. So if you make holes here, like one hole here, One more here, one more. What is pressure? We know it very well. When you go down, you feel high pressure. What it means? The water molecules, you feel pressure in ear mostly. I recently learned swimming. I still don't know, but I can go a little bit down. And I feel it. If you go down, you feel pressure here. So you assume this is a surface area of the ear. Water molecules are actually hitting against your ears. So you go down, you feel high pressure, means molecules are hitting greater. This is what is shown by this equation. Okay? The pressure is, you take any surface area, constant surface area, deep inside, the pressure increases. You go high up in the atmosphere, the pressure keeps on decreasing. Yes.
I don't understand then the difference between pressure and temperature, because you said pressure means, high pressure means molecules are hitting your ear more fiercely, but that's exactly what we talk about temperature as being a higher velocity of different random motion.
Density is also important. Suppose
Okay.
there are two different. That's a good question. Suppose there are two different liquids. Okay. 1, 2. There are 1 million particles here. There are few particles here. Okay. All particles have same kinetic energy, same temperature.
Okay.
And this is your ear. Which ear will feel greater pressure? This one. More particles are hitting. Even if they have same energy, there are more particles. So density is high. Density is low.
Density means
But the temperature is same. Temperature means average kinetic energy of the particle, which is same by definition.
oh,
Where will you feel more pressure?
it's like what you said, P over rho is like temperature.
Yes, P over rho is temperature. P is not temperature.
So temperature times density, that's what gives you pressure.
Yes.
Okay.
Temperature times density?
P times pressure. Yeah.
Yes.
Yeah.
P equals
It's
rho.
P over rho.
Density times temperature gives you pressure.
Yeah. Okay.
Not exactly, but there is some constant.
Approximation.
So you understood this? Here you have greater pressure, less pressure, but the temperature is the same. So temperature is not the only player in pressure. Okay?
Why does the molecules heat more frequently on the
Say it again.
why does because the density of the water doesn't change. Why does why do the molecules water molecules heat more frequently with body
Heat.
or ears? Maybe collide or something.
Oh, so you mean to ask why the pressure is greater in the as you go down? The temperature is this, let's say the temperature is the same.
I mean the density of the water is almost the same, but we just but the collisions are more frequent. How can this happen?
That's because of gravitational acceleration. You want to understand it physically. Mathematically, it is coming because of G. If you put G equals 0, P is P0 everywhere. Okay? It is happening because of G. But I see your point. You want to physically understand, if I understand it correctly, why if you go down in the water, you feel more pressure if the density is same. Temperature is same, density is same, but the pressure is different. Right? That's the question. Okay. The answer is suppose this slab of water here. Your question is, it's a very intuitive question. He means to ask, you take a water slab here, the temperature is the same, the density is the same, why the pressure is higher here? Right? That's the question?
So it means, and I want to ask why it collides more frequently, so the pressure gets higher.
It doesn't collide more frequently, but
Harder.
it behaves like it has greater pressure because every slab feels the pressure of water. It's constant pressure from water from the surface, from outside. So the element of water element at certain height has greater water volume which is pressing it from downward, which leads to increment of its pressure. even if the density remains constant. Water is incompressible, right?
But if the pressure is higher at the bottom of the ocean, you say that the particles hit more frequently here. But if the pressure is higher, the velocity has to be lower than the water, like on the surface.
Water molecules.
Water molecules, yes. So why does it hit more frequently if the velocity is slower?
Why the velocity is slower?
Because the pressure is higher.
So why do you mean pressure is high, velocity is lower?
Because it has to be like when the pressure goes higher, the velocity goes down.
That's a different thing. That's for flowing water.
Oh,
Okay. The confusion is coming from the gas law. P equals to this is not applicable for water molecules, for ideal gases. Okay? Water is not an ideal gas. Ideal fluid is still not an ideal gas, so it's not always applicable. However, I'm not getting the exact question, but the question is why it has more pressure. It is because due to gravity, it is facing higher density of water from upside. So basically, it works like we just saw now. When I draw the piston, you press the piston, the gas is compressed. When it's compressed, you work on the system. So because of the compression from the upper side, all the layer faces the pressure from high side. So this is why the volume element at the bottom shows under extreme gravity that it has high pressure. This is what you feel when you go down.
So I mean, how to understand this in the microscopic for molecules? Are they hitting more frequently, or are there more force when it collides?
They are hitting frequently because they have pressure from outside. That's it. If you are going down, if you are at the surface of the water, you are down below. When you feel high pressure, that means the water molecules are putting more pressure on the area. The reason for that is at microscopic level, they are feeling the pressure from the water from outside. This is why they are more dynamic here. That's the explanation. It happens even in gases. Okay. Now, if you make 3 holes here, okay, how the water will come out?
If it has higher pressure, which is at the bottom, then it has higher velocity. It should have higher velocity, but why? Why does it have higher velocity when it has higher pressure? What's the reason? What's the mathematics I'm saying? I know what will happen.
This is the area.
Yeah.
The mathematics is here.
Yeah.
The physics, the understanding physically is different.
Yeah.
This is the area. Okay. If it is blocked, area is being hit by the molecules.
Yeah.
They are hit strongly. The force applied is more, as we talked about at bottom, because of gravitational acceleration. So this water will go like that. Okay. Make a stream. As you go up, this will fall like that because it has smaller pressure. As you go here, the pressure is even smaller.
But isn't it related to Bernoulli's principle?
Hmm?
Shouldn't it be related to Bernoulli's principle?
Bernoulli principle is always applicable. It is just a special case when the water is not flowing. In Bernoulli's principle, it is true. Only thing is the first term is 0.
Yeah,
Where you have velocity.
squared is 0.
There is no v here.
Yeah.
Of course,
Talk about acceleration. Yeah.
now water is falling here, but here we talked about inside the water. This is how it moves. Okay.
Can you repeat that?
In Bernoulli's principle, we had this equation. Constant. Okay. So when you put v equals 0, This term is 0.
Why is it 0?
Because the water is not moving, it's static. In this section, we are in the regime of hydrostatics. It's static. Of course, when I put a hole, the water is coming out and falling like that, but this is static water. So in static water, the enthalpy is constant. Okay, and in then you have gravity as well. This is basically the same thing that we derived here. So gravitational force per unit mass is equal to 0. So because of this, we put it here, gravitational force, then find out how the pressure will be here.
We have the force, what is the acceleration time? And we have a force here, and what is the interaction time so we get the velocity?
There is no velocity here.
But you have a beam of water outside, it has a constant velocity. The
You
hole
mean
is big.
you are asking about this water? Which
Yes,
beam?
we
Which
have
beam?
the initial velocity is, so it took the water gets out with some initial velocity.
This I explained just to show that the pressure is different, how it plays out. Okay. When we talk about hydrostatics, not on this. Hydrostatics is on this water.
I mean, how does this force make an velocity? Because the water goes out. It goes further because it has a larger velocity. I know that they are proportional, but where is the time come from?
Which time? Time of the
Acceleration time. Time multiplied by force is momentum.
But time of what? What do you mean by which time you mean? You mean the time of the water that falls down or what?
I mean, so the water goes out with some velocity in this case.
Initial velocity.
And yeah, the initial velocity in the units, there's a time multiplier with the force.
So initial velocity with which the water will be thrown out, that depends on initial pressure. Whatever pressure you have at the height.
No, I mean, it has a force, but to convert the force into a velocity, there should be some time.
In the beginning, at t equals 0, when you make a hole, let's say, you just make a hole instantly. So initially, why there was no velocity? Because there was infinite potential, which was stopping it, okay? Like the pen here, okay? So, okay, it's better to understand from this way, from classical point of view. Pen is here, I'm holding it here. So right now, what is the velocity? 0. Why? There's infinite force I'm applying here. Infinite means I have enormous force. Even if the gravity increases, it will not fall down. I'm holding it. If I leave it, okay, it will start falling down. Okay? It will start falling down with velocity v equals 0 in the beginning. It will accelerate slowly. Now imagine there is already a pressure from outside. Okay? But I'm holding that pressure too. You are with me? There's a pressure from outside. Let's say something is pushing it down. And I'm holding it. Gravity is also pulling it. Something is constantly pushing it. Then I remove my hand. The initial velocity will not be 0. It depends on how much pressure it has. Okay? Same thing.
So
Here,
there's another mechanism in the flow.
another mechanism is the fluid pressure. So there are two things which are pulling it downward. One, gravity. Other one, fluid pressure. And once I had the holes packed, it balanced everything. The moment I made the hole or remove this wall, okay, if it had only gravity, then initial velocity will be 0. Because of the pressure, it pushes it down like that. You understood it? Okay. All right. Okay. Now we talk about fluxes. We talked about one flux already, and I explained what is flux. It's the flowing of a certain quantity or any physical quantity across a unit area per unit time. Okay? Any quantity flowing across a surface area per unit time. That is the flux. And in the continuity equation, we knew that this is the rate of change of mass from a system is equal to negative of a flux going out of the surface area. And this quantity represents, or this quantity, rho v, it represents amount of mass flowing out of a unit area in a unit time. Okay? This is unit time, unit area. This is called mass flux. Physically speaking, a fluid has three quantities: mass, momentum, and energy. So when the mass flows, it is mass flux. Similarly, momentum also has flux, energy also has flux. So we proceed to analyze how the flux of energy and the flux of momentum transports itself in the fluid. Okay? So this is the fluid that we always have in our mind, and we found out that if the matter going out of this area, its flux is represented by the density into velocity of the fluid. Now, if it has momentum, momentum is also like a physical quantity like mass. When something moves, like this pen is moving, it has mass, it has momentum, it has energy. All three have to be conserved in specific cases. If there is no external addition of mass, no external force, or no addition of external energy. So how the momentum is transported from a surface, that we call it momentum flux. What is momentum? Mass into velocity for classical particle. Again, we have the same problem for fluid dynamics. You don't know what is the mass at a particular point. So we deal in terms of momentum density. But many times we just call it momentum. But what it means is momentum density. Not like mass into acceleration. It's rho into acceleration. Okay? Sorry, velocity. Now, what is velocity? You will never be confused with the velocity of the particles or the speeds with which they are randomly moving and interacting with each other, and the bulk velocity of the fluid. When we talk about the momentum density of the momentum, we always talk about bulk speeds, like a flowing river. Even in hydrostatics, the water is static, but the particles are always moving with each other. So they have random speeds. So momentum flux is defined how much momentum is flowing out of a certain system in a certain boundary.
Wait, are we still hydrostatics?
No, that was hydrostatics was a special application of Euler equation.
Okay.
So general. In hydrostatics, what will be the momentum flux in hydrostatics? Zero. There is no momentum flow. It looks very trivial statement. Okay. But whenever I talk about momentum flux or energy flux, even mass flux, it's moving. Velocity is non-zero. So momentum is rho Vi. Now what is Vi? Velocity is a vector quantity.
Yeah.
It has three components. Have you studied tensors?
Absolutely not.
No?
No.
You did.
GR.
GR. Okay.
Some of us did. Yeah, it's assumed that you know.
Okay, so what we are going to use is a very preliminary version of tensors. So it's very simple. Okay, we'll go through that. So a velocity has three components. A scalar quantity, density is a scalar quantity. It has one component. Okay. Vectors have three components, and we'll see shortly that pressure actually has its pressure Ij, okay, 9 components, which is we call second order tensor. We'll get to that. So this is the momentum density, or when I call momentum, it should not be confused. It's basically momentum density. Momentum density, momentum is also a vector. It has three components. So I means x, y, or z. In Cartesian coordinates, in spherical it's r, theta, phi. Okay. So our purpose is to find what is the momentum flux in a flowing fluid. So what we need to find is this quantity. Okay.
I is like a generic coordinate, like it could be x, y, z, it could be r, theta, phi, or something like that.
Say it again.
Can I is like a generic coordinate, it could be x or y or z, it could be r, theta, or phi, or whatever.
Yes, whatever.
It's like we don't actually care about the specific coordinate.
No,
Okay.
we don't care about the system we use.
Yeah, okay.
But it's always good to keep one system in mind. Yes.
Yeah, I know you talked about this a little bit before, but you said that when we write dv to the t, for example, we mean the velocity of the fluid going through a specific spatial area or volume.
Yes.
But I'm going over the last lecture, and you wrote here that in Euler's equation, dv to the dt refers to the change in velocity of a specific fluid particle.
Sorry.
Because not a fixed point, instead trying to change the velocity of a specific fluid particle that moves through space.
Okay, here fluid particle doesn't mean fluid particle. Okay, if you look at, you will mostly follow random sheet book. It refers fluid particle again and again, but you should not be confused. It is not particle of the fluid. It means
It's a box that moves.
yeah, it's a volume, a small volume. And by definition, small volume is small enough compared to the length scale of the system, but it is large enough to have many molecules inside. Okay, so fluid particle means volume element.
So
But-
we go with the fluid instead of standing in a specific point and looking at what's changing.
Where here
Mhm.
or there?
Okay, here we're going with the fluid, and here we are staying at a specific point and watching the changes in that point.
Yes. So okay, fluid particle can move in the fluid as well. It depends on what kind of system you are dealing with. When we derived the continuity principle, a volume element was fixed, the fluid was moving. And we saw it that if the volume element moves, you do not get continuity principle, you get something else.
Yeah, it's like the Lagrangian approach and the
Yes.
Euler
Yeah.
approach. Okay.
It's only an approach like it. Okay. So our purpose is to find this. V is a vector with three components. Okay. So let's proceed with that. We can call this let's call this PF, moment of flux. Okay? Simple. So solve this. Now, what is del rho del t from continuity equation? It's minus of this. Okay? Minus. Okay, let's write it now first. Then I will show how to write it in component form. Okay? Plus, and what is del V del T? Euler's equation. Remember? This was the equation. We need this one. Okay. Now we will change the notations. We will not use this standard notations of grad and divergence. Rather, we will use some tensorial way of representation, and there is a reason for that. How do you write divergence of A? Let's say A is a vector.
Usually it's the derivative of minus x plus
X to x, y to y. Okay. What is this? This is vector or scalar? Divergence of A.
Should be scalar.
It's scalar. Okay. So this is basically written as, let's say x, y, z coordinates.
Yeah.
This is divergence. Or what it means is x component with the vector, derivative with x, y component with y, z with z. Okay. But this is also vector. But now we write the components, we don't write the vectors. Okay. So this becomes basically scalar. I can write this as summation of like this. X1 is x1, x2, x3. x1 is x, x2 is y, x3 is z. We can write it like that. And we can remove the summation sign. This is convention in mathematics. Then once you write this represents the divergence. So this is a way of writing divergence. Okay? Similarly, gradient of some b. Now what is b? B is a scalar. Gradient is always of a scalar. This can be written as. But now, how the gradient is defined? All three components of b have to be. So b has to be with x and y and z altogether. Okay.
What about the heads? The x and y heads?
They are unit vectors. No? There's no.
The summation for.
No. Basically, you don't even have it here. Okay?
Oh.
This A is a vector. Dot product with
Yeah.
cap, so it just goes away. Basically, it's a scalar.
To write the vector there, you don't need the ax, y, z in the vector representation. Just
Yeah, in the right hand side you don't need it. Okay. So the cap was not required. Alright. This is a scalar. This is how we write it.
Yes.
Okay, so we will use these types of notations when we write divergence, and we write it in that form.
So, is this independent of coordinates? Can I use this? Like this specifically for Cartesian coordinates. I know eventually with tensors you want to be independent of coordinates.
You can use it in any coordinates,
Correct.
but you have to, when you transform it, the transformation laws have to be kept in mind. The Cartesian coordinates are the simplest ones.
Yeah.
Okay, so let's write the continuity equation and the other equation in this form. These are the same things. I just wrote the divergence in that form. And this is
Wait, you didn't finish the gradient. What does that look like?
how? I'm writing it here. I've written it here.
Yeah. But
This is Euler equation. Okay. dv dt is minus v dot grad. So grad means d or dxk, vk and then vi. So basically these are, when you expand this, you have to use the same for them. V, the k component of v equals the k component of x, and then three separate components of v. And same thing here. So basically, this equation is ith component, the rate of change of ith component of velocity with time. This is Euler equation. Okay. So we will use these two notations instead of the previous ones. This is v dot grad. Okay.
this is the v dot grad times v.
Not times. It's operated on v. Okay. We use these notations and write this equation there. All right. Okay. Let's put the center. take this row inside. Taking this row inside. Row here. This row cancels.
How did she go from there to there?
I just go from here to here. I had divergence of rho v here. Divergence of rho v is written in this form. Okay? This is what I put there. Okay. In second term, I have gradient of p by rho term. This is gradient of p by rho. First term. And then second term you have a v dot grad v. This is v dot grad v. Same things. This is not I, this is k. Because we are representing gradient in form of k, so this is dp dx k.
So it's saying for each coordinate I, we have to sum over all coordinates k.
Yes.
Okay, by the way, then why is the on this left side of the equation, why is it rho inside the derivative like it is in
What?
Yeah, here. Why isn't it is the del rho v over del xk like you wrote it on the left side of the board? The rho should be inside.
No, you can put it inside, but how does that matter?
Because it's a
Rho doesn't have components. V has components.
Oh,
V has 3 components. Rho is scalar.
yeah, but should xk represents like x, y, or z. I can say the rho over the z or something like that. That makes sense. So vk over. You just wrote over there inside, and now it's that's one.
Yes, but when you write it in this component form, rho comes out because at a particular point, that's a particular point, you put the value of the rho at a particular point and we show like that.
Oh, okay, so it's not the derivatives of the different components.
Yes.
It's constant in that, but shouldn't.
Just because rho does not have components. Alright. Now we do some experiments here. This. We write pressure like this. Why? Because the equation has I component, basically I. We are starting with the I component of momentum, but here we have K. We are defining it in terms of K, so we have to represent it in this form. What this means, del Ik, which is a Kronecker delta function, it is 1 if I equals K, it is 0 if I is not equal to K. Okay? It basically means pressure is isotropic. It has only, this term is defined only if I equals K. We'll come to the physical meaning of this.
Can you explain the change in the index again? Why you change from I to K? Is it what K represents what?
K and I are same things basically, but in the equation you look at this term. What does this show? The K is summation convention. You add 3 dvx1 over dx1 plus dvx2 over dx2 x3 over dx3, but the main component is I. So the equation actually represents the left hand side is I component of momentum density. Okay, so you have to represent it in certain manner that this also becomes the I component. So mathematically, the way of transformation of the coordinates is this. Okay, it's just mathematics. There is no physical change here because we define the gradients in this form: dxk, dxk. Okay. The gradient is in this form here. The same thing here, but here the k, we call it summation convention. This contracts. I remains here, but we don't have it here. So mathematically, you have to transform it, write it in this form. There is a reason why we write it in this form. There is no difference. But we'll just get to that why we did that. There should be reason of way of representation of things. Okay? Okay, so we have two terms here, this and this. You can see there's rho v, del rho v k dx k, and rho v k outside. Okay, you don't need to take this rho necessarily outside. It's basically the same thing. You write in this from here. Okay. Okay. This is what your question was. Fine. Because we have to contact with this. Rho v k, rho v k. Rho actually changes with coordinate. Always not confused. Rho depends on coordinates, even if it's not a vector.
Yeah.
So you have two vectors here. A dot del b over del x, b dot del f del x. Right? So you can write them together. These are two terms. Minus I just combine these two terms here. Okay. Separate them out. You get the two
Oh, it's
terms.
like a multiplication.
Hmm?
It's like a derivative of.
Yes, yes. Two derivative terms. Directly.
Do you assume incompressibility?
No.
So why can you put the row into the?
No, it was.
Nee, rho was inside. I made a mistake to take it out. Rho is anyway
Oh.
inside. Okay. I put it outside and it was a mistake. Is it okay?
Wait, this isn't a dot product because it's we're talking about just the I component. So it's a scalar.
What? Which dot product?
No.
You mean why did you put the dot here?
Yeah.
It's not a vector dot. It's just multiplication.
Yeah.
When we write in terms of
because
coordinates,
it's one coordinate.
there is no vector representation. Alright. Minus, we write this term here, which is del I k. Alright. We are almost there. Now, this is just a Kronecker delta function. It has value 1 or 0. Okay, so it is not affected by the coordinate itself. But we have the derivative along the same coordinate x k, x k. So we can combine these two as well. So that is pf equals minus now, how this delta came inside is just a unitary function, just 1 and 0. So took it inside. Okay, so this is the derived expression for momentum flux. Now there is a peculiar representation of this term inside it. It is called momentum tensor. Okay, pi I. How many components this tensor has?
It's like 9.
9 components. Each 3 for I and 3 for K. You can write all the components. 1, 1. Now, P has only 3 components when this I is equal to K. Otherwise, P is 0. These are the 9 components. I didn't make a mistake. Okay. So you can see pressure is only in the diagonal terms. So this is mathematics. Now we try to see its physical meaning.
Why do I need this?
Huh?
Why do I need the tensor? Can't I just get a formula for VI? It's a sum of the 3 Ks. That's what we wanted in the first place.
You can deal with this long expression.
No, we got the expression at the top.
Hmm.
The over the xk.
This one.
No, that one.
This
Yeah.
one.
We wanted the derivative. We wanted in a coordinate I the momentum flux. We added this k because we are saying we'll sum over all k's. Why can't I just write over x and y and z and then
You can
use
write.
that?
You can write.
Okay. Like
This
just
is
sum
also
over the
correct.
row of the tensor also.
Hmm?
Like just sum the row of the tensor. If I want for one specific for coordinate I,
You sum over K.
yeah.
This is sum over K.
Yeah.
Okay.
So why do I need to separate? Why can't I just use them as a sum?
This is sum. This is basically what it means.
I'm trying to say what's the use of the different
In tensor notation.
things separately. Why do I need it?
Separately this one. There are 3 components.
Yeah.
Tensor has 9 components.
Okay.
It has 9 components, so we need 9 components. What do you mean?
Is there a use for one of these variables alone, or are they only
Which
used?
variables? Which variable?
I don't know. One of the things in the 3x3 grid.
Matrix, yes.
Yeah. Can I use? Is there any use for one of them specifically, or are they only used when I sum over a row of them?
No,
Because
no,
if
no.
that's the case, I will just use that expression.
No, it has difference. Okay.
Okay.
We'll see it.
Okay.
What is the physical meaning of that? It has many physical insights. If you write it in this form, this energy moment, this momentum tensor,
Okay.
you try to understand how the momentum flux behaves in the system. Okay?
Yeah.
Moksh. So we've got PF as a vector actually, because we take a divergence of this tensor, so shouldn't it be a tensoriality?
Yes, it's vector.
So what did we lose? Obviously, it's vector. It's a vector.
Yeah.
Okay.
This is I component. It's PFI.
Okay. But you should
the index should be.
the momentum.
What?
Yeah.
Not
Not
the
upward.
It's right.
momentum.
Okay. Because F was written downwards, so I wrote it there. We don't need to worry about the contravariant covariant tensions here. Okay? We don't need to worry about that. Which is okay. Everything is downward. Yeah. Okay? Mathematics is fine. Now the physical inside. Okay. What this represents? Like we saw that how much mass is. Okay. So this was okay. Now we take the volume integral of that to understand its physically. Okay. I just did the volume integral left and right hand side. Now I can convert this. I can convert this into surface integral. Now we understand what it means. Left hand side is, if I write it again here, you remember the continuity equation here? There was a representation of this equation in forward. Remember this equation? What this means? Explain it to me. Yeah.
The change in volume must come through the boundary.
What?
Any change in mass, which is like the change in when you integrate density over time, over the volume. Must
Not
come
density.
from
Whatever mass is going out of a certain volume.
it must become out of the boundary of the volume, because the integral of the flux aligned with the volume must be. If mass decreases, it must decrease through the volume. It must go
Right,
out.
right.
Must
But what this means? This means
can be created.
that the mass which is flowing out of a certain bound volume in a unit time is equal to the mass which is flowing out given by this mass flux. Okay? And now look at this equation. Instead of rho, what I have? I have rho Vi, which is momentum, basically momentum density. So the mass that goes out of a certain volume, mass that the volume loses, has to be equal to the total flux of the mass which is going out of the system. Similarly, the amount of the momentum which the system is losing is equal to the flux of the momentum which is going out of the surface. It's precisely the same. Okay?
Okay. That's cool.
Is it clear?
So this momentum is a tensor. It's defined over like every point in space, and you can use it to describe the flow of momentum in and out.
Yes. Any volume loses, this is the flux of momentum in a flowing liquid.
Oh, and for density, we had when we described the flow of mass, we just had a vector because mass is a scalar.
Mass is scalar.
And we need just a vector to describe. Now we have a vector, so when you describe for each component of the vector which way it is flowing. So that's why we have free vector.
It is little more intuitive than that. I will explain now.
Okay.
But the mathematical form should be clear. Okay.
Yeah.
So what does pi ik mean? If you have liquid moving, same picture we have. You take any surface area. This is amount of momentum. What is the definition of pi ik? It's the amount of momentum flowing out of a unit surface area per second.
This is the
Same like rho v here is the amount of mass flowing out of a unit surface per unit time per second. Here the amount of momentum which is flowing out. Okay. Last thing. Okay. Last thing to understand is second rank tensors physical meaning. If you have a cube, now we need to have a three-dimensional picture because we have second rank tensor. Okay. What is the meaning of pi ik? Now we understand what in total what pi ik is. It is the momentum flowing out of a unit surface per unit time. Now what is the meaning of, let's say, pi 1 2, pi ik, pi 1 2. This one, let's say this one, pi 1 3. What is the meaning of that? 1 is x, 3 is z. You explain that? What is the physical meaning of one component of pi 1 3? It's like it has two components. How you visualize a tensor? You can visualize a scalar. This is density. It has no direction.
Yeah.
Zero-dimensional vector.
Like a height or a number or a color.
It is density. Let's say density, mass, whatever. Pen is a scalar. When it moves in a certain direction, you have its physical notion as a vector. It is moving in this direction. It has this. If it has three components, x, y, and z, you can have it in mind. How to visualize the second rank tensor?
This is describing the rate of change of a vector. Of like,
There is no rate of change of vector. It's vector. It's kind of vector, but it has two components. Vx means x component of velocity, right? Pi xy. What it means?
The surface that is perpendicular to the y surface.
Right, but little more.
The influence of one component about movement in another.
No.
how much the x component, how much the velocity in the x component is.
There is no velocity. It's certain vector.
It's like when we have a mass and a flux vector for that mass, we say the y component is how much mass is flowing through the y-axis in the y direction, like the shadow of it on the y direction.
Which is xy.
Yes, so
You
we're
have to be
talking about
specific.
the x.
You have to be specific about this.
velocity.
What does this mean? Okay. This means, let me explain. Momentum also has three formats. Momentum is flowing. It is flowing in all directions. Momentum is a vector. Okay, momentum is a vector. Momentum flux is a tensor. This is not momentum. This is momentum flux. So it means pi xy means this is x. y, z. Pi xy means x component of momentum,
Y direction.
not y direction, across a surface, he said it correctly, which is constant in y, like p of x. Okay. Now, which surface is constant in y? This is y. So, we have many surfaces. This. Which surface in this and behind? Which surface has y equals constant?
Top and bottom.
Huh?
Top and bottom.
Top and bottom. This surface, let's say. Okay. So pi xy means x component of momentum, which is rho vx, right? X component of momentum, which is flowing along this surface, constant y, basically constant y surface passing through this surface. Okay, this is the physical movement.
So when you move in that direction, x component of velocity will increase or decrease based on pi xy.
Say it again.
So if you move in that direction, like if I'm looking at the momentum here and the momentum there, and looking at the x component of it,
Only x component.
yeah, and the rate of change I should see is pi xy.
Yes. X component of momentum, just x component, how it is changing at two different points along y coordinate across the constant y surface.
Yeah, when I change, yeah.
But why it is needed? Last point. Give me any example where you have one component of vector changing in another component. Huh?
I remember the word. I don't remember the word. Turbulence, maybe.
Hmm?
Turbulence? Is it necessary?
Curl, you mean curl. Fine, curl is, I'm talking about very simple case. It's always empirical. Any function that has three components and all the components vary in different components in different manner, it will have all the dependence. Okay? So a typical example that is given in textbook is solids. When you apply pressure on solids, they deform in another direction. Okay? So that's the way to look at it. Put pressure in one direction, the change takes place in another. So you have to take care of. This is why pressure is a 9-component term, second order tensor. Pressure is not a scalar. We can treat it as a scalar if it is isotropic.
What does that mean?
Okay, nice. Why pressure? Okay, this tensor is symmetric.
Yeah, because
This term is equal to this term, right? V1, V2, V2, V1 is same. So this is called symmetric tensor. This term is equal to this term, and this is equal to this. Okay, so this is a symmetric tensor. Again, the pressure comes only in diagonal terms. Why? Pressure may not come in diagonal terms. Pressure can come everywhere in general.
the diagonal values represent if I am looking at the x coordinates and moving in the
x-axis itself.
So it's like, how much am I going to accelerate along this axis that I'm moving on? It's not something that's orthogonal to that. So that's acceleration.
Why pressure is coming only in diagonal terms, not anywhere else?
Because pressure can't make you accelerate in a diagonal direction.
Pressure can, but why it cannot here? It goes along with certain assumption that we have been assuming from the beginning. Pressure is isotropic. It is same nature in all directions.
Same.
At certain point in gas,
Oh, we assume it's a number. You don't have to represent it as like a function.
yeah.
And
This is why we many occasions we treated pressure as just a scalar.
Okay.
Why? Because it is isotropic. Assumption is that pressure is isotropic. It's a very standard assumption. It works almost everywhere, but it is not God given. There can be systems you can generate where the pressure is not isotropic. But in all our systems, pressure is isotropic. What it means? It means you go deep down in water. You know swimming, deep down. You put your ear this side, or this side or this side. you feel the same pressure. That's what it means. Okay? So we go with the assumption that pressure is isotropic. It doesn't necessarily have to be. Okay? There are systems in astrophysics where the pressure is anisotropic. The anisotropy is caused by some external factor that we don't consider here. But all systems that we consider here, we go with the assumption that pressure is isotropic. Now, what if pressure is not isotropic? What will happen to this momentum tensor?
Wait, can you repeat what is the connection for the asymptotic systems?
There is no isentropic, isotropic.
Isotope.
Isentropic and isotropic are entirely different.
Yeah, I thought you said isotope.
Fine, I said isotropic. It's not, system is not isotropic. The pressure is isotropic. What it means? It means in this room,
Same pressure for another.
you put an area here, there's a pressure. You put here, here. So the pressure that the area faces is direction independent. Okay? This is what it means that the pressure is isotropic. Once it is isotropic, you get only the terms of the pressure where I is equal to J in the same direction. Okay?
So isotropic just means rotation and gravity.
Rotation invariant what? Pressure.
Okay, no, it's not.
It's isotropic even in the fluids which are rotated. Okay? Pressure is always measured. Okay, I have a question. If the river is flowing like that, the water is flowing. Yeah, this is important. If I put my ear, this is my ear. We go in terms of ear because so that we can physically realize. Like I'm lying down and putting my ear like that. I will feel some pressure here. Okay. You will always feel pressure. Water is always there.
But you're perpendicular to it.
Doesn't matter. You are inside the water.
So it's like motion.
You will always feel pressure in all directions. Okay? You will always have pressure here.
But you wouldn't have the pressure that comes from P from the gradient pressure. That's what causes the bulk motion. That's why P is only on the diagonal.
Bulk motion is there,
Yeah.
caused by anything, gravity or pressure gradient. In a localized region, you have isotropic pressure.
Is this scenario similar to what we were talking about before about phi xy? Can I think about it like the direction of my plane and the direction of the flow or the direction I'm looking at currently?
Direction of the flow is this, okay? And your plane can be anywhere. Your ear can be here. Okay, we will get to your confusion. In which case you will feel more pressure? This way? But now I said pressure is isotropic. You should feel same.
But you have this P term.
Yeah, there seems to be some confusion here. If I put my ear against the direction of the motion of the water, I feel more pressure. And if I do like this, the pressure is less. But what it has to do with isotropic? Now the pressure doesn't seem to be isotropic. What is the problem here? I said that the pressure has to be isotropic. It is same in all directions. But at the same time, when I'm giving this example, it appears like you will feel more pressure here because the water is flowing. You will feel less pressure here because it is water is not flowing.
So it seems to be contradicting statements because
Yeah,
pressure
there seems to be
but
contradiction.
when you change directions, it suddenly.
But it should not. So, can somebody guess what's going on?
Maybe if you move with the fluid.
Hmm?
Maybe if you move with the fluid.
Right. So, the thumb rule is pressure is always measured in a co-moving frame.
And what?
Co-moving frame. It's called co-moving frame. Pressure is defined. So the person who is measuring the pressure has to be moving with the fluid. Otherwise, pressure is not defined. Okay? It's very important. So now, if the person is moving with the fluid, he will feel the same pressure.
Yeah. Because all the beats should cancel out.
That means the pressure is isotropic. Okay?
Wait, but why it solves the problem?
Hmm?
How does it solve the problem? Why?
Okay. So previously, what the problem we had is, if you stand like that,
Yeah.
you feel more pressure. If you stand like this, you will feel less pressure. So the pressure is different. It cannot be. Now imagine you are flowing with water. Okay? If you flow with water, you will not feel high pressure here. It's still same in all directions. That means the pressure when you measure, suppose your ear is measuring the pressure, it's pressure measuring machine. It means that it measures the pressure precisely only when you are moving with the fluid. What is the meaning of moving with the fluid? That means
V is 0.
That means no V is 0. V is bulk speed of the fluid. Your velocity at the local point has to be equal to the velocity of the fluid. What is the velocity of the fluid in a for a co-moving observer?
0.
No.
Why?
Fluid velocity is an absolute velocity. It's not inertial frame. That's a different problem though. In a co-moving observer, if it is pressure gradient, in his frame also, the fluid, he will see the fluid is static. But when he studies the principles, Euler's equations, the fluid has bulk motion. Now there is a difference between a moving car and a flowing river. What's the difference? A moving car is an inertial frame, right? Constant speed. A moving car or moving train at a constant speed is an inertial frame. Inertial frame means the laws of physics remain same inside. But a moving fluid is not an inertial frame because there is nothing which is static, everything is moving. Okay, so it's not defined. So even if for a co-moving observer, he knows that this fluid has a motion because there is a pressure gradient. He can measure the pressure gradient, right? For a co-moving observer, suppose the pressure is increasing like this and the fluid is moving. A co-moving observer, he will see the pressure difference. But when he applies this Euler equation, he sees that there is a pressure, there is a pressure gradient. But in his term, the acceleration is 0. That's a problem. So it is because a moving fluid is not an inertial frame. However, a moving car is. These all are just physical ways to look at the fluids. So these are very important. What time is it? 6. Want to take a break? We did take a break today. So we take a break of how much we have. It's 1 hour. It's an Indian time here.
Technically, we have until like 6:15. If you give us a 15
Now it
break.
is 6. It should be. Is it what time?
It's like 15 minutes. For every hour.
Okay. Then we meet at 6:10. Okay.
Okay.
And then when the course ends,
7 o'clock. That's the time, schedule time, right?
it's not actually. We're supposed to have 15 minutes at the end for every hour. So
The
like
total
for
time is
lecture
2 hours and the quarter, not.
if on the schedule is 3 hours, we're supposed to have 45 minutes afterward. So if you like give us
45 minutes or what?
the lecture is supposed to take 2
Every hour is
hours,
actually
15 minutes.
3.
Okay, okay. So 3 hour means you mean 45 minutes of break, you want 45 minutes of break. You're tired.
I don't know. We could do like a shorter break and then finish earlier. Like that's what usually happens.
So we study the momentum flux. Everybody's here? Okay. How the momentum flows from the surface. Now we'll go to energy flux. Similar to mass and momentum, energy is also physical quantity. So you consider the same pound volume. Energy contained inside this volume is the sum of
We're talking again about a non-moving volume space.
yes. Volume space is not moving, fluid is moving.
Yeah, fixed one.
Tension. You were in the class before? The new student or just volunteer?
He was here.
Ah, you were here.
Thanks.
Okay. Okay. So now we talk about energy. Okay. Basically, energy density. Because in fluids we deal in terms of densities. The first term is the kinetic energy density. Second term is internal energy density. Epsilon is internal energy. Now we need to review our knowledge of thermodynamics here. Because we know that most of you do not have knowledge of thermodynamics. from the perspective of this course. So we studied in last lecture that if you give delta Q energy in the system, heat, what does this do to the system?
It goes either into internal energy or kinetic energy, or
It changes the internal energy, d epsilon, and
it could be the internal and it could do work.
it can be work. And work, we showed P specific volume, and we wrote it in this form. Okay, this is what we studied in last lecture.
This is the field law.
This is the first law of thermodynamics. Okay. First law of thermodynamics. Today we will need second law as well.
But this is not the classic form of the first step.
What do you mean by classic form?
Right?
This is the very standard classic form of the first law. Which form you are aware of? First law of thermodynamics is energy conservation principle.
This one.
You divide it by unit mass.
Yeah, when you asked it, I was
It's
not
divided
sure.
by mass.
This is what I get.
Yes.
It's divided by mass, that's all.
Well,
Yeah.
the mass.
Ah,
And the
Per unit mass.
okay.
The P sub P, V sub Q, or
What?
something like that. Oh.
Okay. So this is the first law of thermodynamics, which is basically energy is conserved. We use this because we are studying the energy flux. Energy flux. So motivation is if energy is given, energy density is given, and the fluid is moving, what is the flux of energy that goes out of the surface? We have the same question. The mass is given, density is given. What was the mass flux? Continuity equation. What was the momentum flux? We just studied now. What is the flux of energy? Okay. And we knew that when we had insight of momentum flux, we had a very good physical insight of what it is. Similarly, you will have physical insight of what energy flux is. Okay. So this is also okay. So what do we need to find? Again,
D over dt, right?
yes, del over del t. It's important to say it's del over del t, which is, so we take the first term because it's very lengthy expression, it gets very lengthy, so we deal with terms one by one. If we take the first term, okay. Now we have derivative of density. This comes from here, and derivative of velocity. This comes from here. But we will not write it in this form. We will write it in a old form. What is the expression del v del t? Okay, and okay, Euler's equation. So we replace this and this from here into the equation there.
Now we develop another tensor for the energy flux.
We will not need a tensor. We will not need a tensor representation of energy flux. We'll see it.
Because it's scalar. Because
Energy is scalar. Momentum is vector. So the flux of momentum is momentum. Second order tensor. Energy is scalar. The flux of energy is vector.
Okay.
Mass is a scalar. What is the flux of mass?
Flow, just flux.
No. This is
Rho
flux
V.
of mass.
Yeah.
Vector.
Mass flux.
Okay. Mass is scalar. Flux is first order tensor, which is vector. Momentum is vector. Its flux is second order tensor. The energy is scalar, so its flux will be vector. We'll see it. Okay. All right. Now, this is the first law of thermodynamics. What is the second law? What's the physical meaning of second law? Nobody used to be thermodynamics. You have heard of it. Entropy always increases in the universe. That's the second law.
We just started it. Like,
Hmm?
we just started it this week. They were talking about the number of microstates in each situation.
Yeah. Number of macrostates are for a system where the number of macrostates are maximum, the system makes us into excess. Yes.
Okay.
A particular state. Fine, but we don't need to go that much into detail. And there comes concept of entropy. And rate of change of entropy of a system is dq divided by dq is the heat. dq is always the heat, not energy, heat. Heat is energy, of course, but it's heat, external energy which is given to the system. So dq becomes TdS. Maybe in next lecture we'll have a detailed discussion on what is the physical insight of entropy.
Wait, so what's T? If Q is
T is temperature,
But Q is temperature. So dq is change of temperature.
dq is heat,
Oh,
changing heat of the system. At a particular temperature, you give dq amount of heat to a system, keeping the temperature constant, its entropy changes by that much.
heat is measured in joules, like it has units of energy.
Huh?
Heat is measured in energy. in
Heat is
joules.
energy, joule. Yeah.
Okay.
Joule per Kelvin is entropy. Okay? Now, we come to the previous expressions. Enthalpy equals V by rho. Okay. This is enthalpy, heat function per unit mass. And the rate of change of enthalpy was this we used before. Now we take, using this equation, so 1 and 2. We want to find what is dE. Replace dq with TdS. This is TdS from here. So dE is TdS minus P over rho square plus TdS now put here. This here. These two terms cancel. Okay. We are left with dW is TdS plus dV by rho. We want grad P here. From this, I write which I can write it as grad P over rho equals okay. So we use this expression instead of grad P here. And we also know that this V dot grad V this you remember from last lecture. This expression and this expression, okay? So we need to replace V dot grad V here and this grad P here. Let's see what we get. Okay. So now we have two terms of gradient. So one term this one term this one. So I write both these two terms together, and the other two terms I can keep as it is. Minus
Just a question.
hold on. Yes.
This is not assuming any sort of enthalpy or anything like that, right? This is not assuming an isentropic system. Sorry.
We will assume later on.
Okay. This
Right
is
now it
in
is general.
general.
Right now it is general.
Okay.
This is why the entropy is coming everywhere. All right. So this is the first term only. Okay. Now we need to work on the second term. Let's do it here. This is first term. Second term. Second term is del T rho E. Okay, which is no. Okay. We know B is this. So how this function transforms? Pull D from there. One row cancels. Can you distinguish between P and rho?
Yes.
What is this? What is this?
Enthalpy.
Yeah.
A bit.
this was equation 1 and this is equation 2. We need to combine both of them. So okay. I remove this part. Don't have space.
Just a question. Shouldn't it be at the bottom, the very, very bottom right of the section? It says PVT grad S. It's like V dot grad S, right? Because they're both the vectors.
Yes.
Okay, so it's mine.
It's T. Grad is always vector. Okay. What is this? Del dot LT? From continuity equation?
Yeah. Divergence of rho V.
Yes. Okay. Now I remove this part. This is minus. Okay. Minus. Okay. Concentrate on this term. Both these terms contain entropy.
Wait, you wrote that it's the derivative of rho epsilon. Isn't it just total E? Because you wrote both expressions here.
Oh, sorry, this is. Sorry, it's not true. It's just the second term. Okay. Okay. Concentrate on these two terms. These two terms contain entropy. Okay. There's a reason why I kept entropy all together, so that you can understand how entropy change behaves in isentropic systems. So this term is rho T.
It's like the continuity equation
Yeah. Something like that, but continuity of what?
of entropy.
Entropy. Yeah. This is why I
You
wrote
have the
this.
S-T where we had the order to
Right.
and then you have
Del S over del T plus divergence of no, not continuity equation.
yeah, right.
Yes. Okay. Now I showed several times that what is this? You can take out S. This is an operator. Okay. What is this operator? This is d dt. Del t plus v dot grad. This is d dt. Right?
Right, because you have dx, dt times, yeah.
Sure.
From Reynolds.
No, there is no Reynolds. Reynolds displacement theorem was applied somewhere else. This is the operator, total differential operator. So I can write it like that. This is rho t ds over dt. Okay. Now for isentropic systems, ds dt is 0. Okay. There is no change of entropy. Why?
Because it's reversible.
Isentropic systems are reversible. Adiabatic systems may or may not be reversible. But it's
So if you have like a bunch of like balls in a cube easily out of order and they become disorderable, then that's a change in entropy. That's not reversible because that just wouldn't happen.
but that's adiabatic.
If they were already mixed, that would be isentropic as well.
99% systems, or even 99.99% systems, which are adiabatic, they are isentropic as well, which confirm two quantities. One, they are reversible. Second, they do not exchange, their energy remains constant. Entropy is constant. Okay, entropy remains constant.
Except for that first instant where the system starts off ordered and then becomes disordered. Once it's disordered, it's isentropic, you can say, because it can't lose any more.
That disorder as
I'm just
a
thinking
measure
about-
of entropy is not, it has problems. Okay?
Okay.
It is very famous, but it is physically, it has mistakes.
Yeah, that's the problem with instant thermal. I'm just thinking about the common example of like balls in a cube.
That this is how you think in terms of entropy as well.
Okay.
If you take a glass, like, then generally you think like this. If the disorder of a system is a measure of entropy.
Okay.
It's not always true. You take a glass in your hand, it has certain entropy, throw it, it breaks apart, it has the same entropy. Now this is disordered. That's a topic of, maybe we can cover it in the next lecture in the beginning. I will give you some physical insight about entropy is. But here, for isentropic systems where there is no heat exchange, the entropy is 0 because dq is 0. No heat exchange in the system. No heat is exchanged, the change of entropy is 0. So this is 0 for isentropic systems. So now we enforce the assumption that the system is isentropic and these two terms go to 0. Okay?
So this came naturally, or did we decide to enforce this?
We decide to enforce.
Okay.
If it's not isentropic, you have to keep all together.
Can you explain again why it equals 0?
Okay. This term is equal to this term. It is rho t ds over dt. Now isentropic systems are the ones that do not exchange heat from outside. They are insulated, like a thermos flask. I gave you example of thermos flask in last class. These are thermos, insulated walls. They do not exchange heat from outside. You cannot transfer heat to system. If you put hot water, it remains hot for 12 hours, or in ideal system indefinitely. So if you put hot water here, air was cold, and you close the lid from here, heat exchange takes place within the system itself. Heat goes from here to here, but there is no heat from outside. No heat comes from outside. Okay, this is restricted. So there is no exchange of heat. No exchange of heat means no change in entropy. Net entropy is constant. No change in entropy means ds dt is 0. Okay. So now we enforce if the system is isentropic, these two terms go to 0 altogether. Okay. Because these terms are basically the same to this.
Yeah.
Now I divide it. Now I think we have two terms with divergence of rho v, right?
Yeah, it's over the level.
Minus plus sine half v square. first and the last term. The remaining term is minus v, right? Okay. So this is a scalar. This is a vector. This is a scalar, and this is a vector. How do you open this? B is a scalar, A is a vector. Okay. Plus this is similar here. This B, divergence of A minus A dot gradient of B. Okay? I can combine both of them like this. So it becomes minus divergence of left with single term. The left hand side is this reminds you of something? Continuity equation. Where is continuity? It's always with us. Continuity equation is always with us. This del rho over del t. I can take this term this side, make it plus, equals 0. Okay? Continuity equation was del rho del t plus divergence of rho v equals 0. Mass flux. Energy, this is flux of energy. Same thing.
Isn't there a name for half v squared plus w? We called it something. We called the thing in the parentheses something. Half v squared plus omega.
Bernoulli parameter. This is Bernoulli. This is Bernoulli's theorem, right? This remains constant. This is Bernoulli parameter. Basically, it represents energy.
What?
It represents energy.
Okay.
What is W?
Internal energy.
Plus
Plus the work that has
work required to displace the system.
Yeah. Wait, so
And
W
what is this?
kinetic energy. Wait, but W doesn't usually include kinetic energy? I thought internal energy includes kinetic.
No, it isn't.
So it just includes heats and stuff. Heat and
Yes,
stuff.
yes. W is equal to,
Okay.
there is no kinetic energy here.
Okay.
A co-moving observer will observe what kind of energy it will have at a particular point is per unit mass, of course, W. And then you have the kinetic energy, so it becomes a total energy. Okay?
But we call the W the density of enthalpy. So we call this density of energy. This Bernoulli parameter thing.
No, it's not density of energy. This, whatever written here, it is divided by density. So it is energy per unit mass.
Okay.
Okay? This is kinetic energy per unit mass. Half mv square is kinetic energy. Divided by mass,
So why isn't this constant? Because energy is conserved.
so it's constant. This is why you have the energy, whatever energy is going out, this is the flux. This is not constant. It's rho v is different.
Wait, but that means that energy flux is just mass flux.
Huh?
That that means that energy flux is equal to mass flux times the constant, like the vector is the same.
Not mass flux. It's kinetic energy as well. Where is mass flux?
Well, you said that the
This is mass flux.
Yeah. So it's times a constant over the system.
Yes.
So energy flows in the same direction as material, as mass, because V. Oh,
Yes. Because what represents the vector here?
yeah. Okay. Just V.
The whole vector is represented by just one quantity, which is V.
Yeah.
Both in mass flux, in continuity equation, as well as in energy flux. The vector is represented by single quantity, which is V. So whatever is the direction of V, that is the direction of the energy flux. But that is not necessarily true for momentum, right?
Yeah.
Because momentum in itself is a vector, so it's a complicated thing. It's non-component. Okay. So this is energy flux. And what is the definition of this? What is energy flux? If somebody asks it. What it is?
The direction that energy flows.
Direction?
Vector. Quantity.
Direction. Direction is direction. Is it direction?
Okay. It has magnitude too. Yeah.
Define it.
If energy flux goes from left to right, then energy in the system will go from left to right. I guess.
That is the principle. What is energy flux? What is mass flux? Mass passing through a unit area in a unit time.
Yeah.
Momentum flux, momentum passing through unit area unit time, but it has 9 components complicated. Energy flux, same thing. Amount of energy passing through a unit area in a second is called energy flux. Okay? A system has 3 fluxes. We covered all of that. To see if something is really important. Okay. This is sometimes represented as JE. In my notes I have written as JE. Energy flux. Okay? Which is vector quantity. I think we are done. Any questions? Yes.
Oh, later you can finish.
Okay. So this is what we covered today.
I see we left the tensor notation somewhere when we went to the energy flux computation.
Say it again.
Well, we lost the tensorial notation somewhere. Is it for a reason or?
Yeah. I explained. Because it's a vector. You write it in tensorial notation, you just have
No,
this.
no.
Yeah.
Of course, it's a vector, but we wrote it in a tensor notation, like the divergence wasn't with nav, like it was
Yes.
dot to the x side.
So you write it here as well. There is no problem. Why we did not write it? We were forced to write it for momentum flux because momentum is tensor. Momentum flux is tensor. This is why you can write the momentum in this form as well, but then it will turn out to be horribly long this expression. So we made it compact. It's just what mathematical function you use in what requirement. You do different things at your home, use different tools for different things. So if needed, what tool is best for what?
Yeah. So
Basically same thing.
okay.
We needed tensorial representation for momentum flux because it's 9 component tensor. We needed compact notation. But it can be shown in the same way. There is no problem there. Okay? Anything else? Attendance.